Okay, welcome to 2.2 Motion in Two Dimensions, the algebraic approach. So in the last lesson we looked at how to solve 2D problems using scale diagrams, and my main comment on that is that it's not very precise. You saw that we were measuring things and the numbers aren't perfect. It's a lot better to use a method like this method that will give us exact numbers. So to use this method, we need to add perpendicular vectors. So when we're adding two perpendicular vectors, perpendicular meaning they're at right angles, we can just use basic trigonometry. And what I mean by that is we can use the Pythagorean Theorem. The Pythagorean Theorem and the tan ratio. So the first piece of that is using Pythagorean theorem to find the magnitude. So remember, when we have two perpendicular vectors like this, if I want to find the result, well, if this is a, b, c, we can say that a squared plus b squared equals c squared. So that's a pretty straightforward way of finding c, the magnitude. And for the angle, theta here, we can say that tan theta is equal to a over, well, in the picture I drew actually, it will be b over a. So tan theta equals b over a. And that means that we can get theta as the tan inverse of b over a. Okay, so we'll look at an example where we're taking two perpendicular vectors, and this says a jogger runs 200 meters east, turns at an intersection, and continues for an additional displacement of 300 meters north. What is the jogger's total displacement? So I can draw this picture here. I have 200 east, I have 300 north. So I want to get my total displacement here. This is my total displacement. And you can see I have a right angle in the bottom right there. This angle here will be theta. And then I can use the two methods I talked about above. So delta D is the square root of 200 squared plus 300 squared. And that's 360 meters. Notice that I didn't draw an arrow on this one because I'm just looking at the magnitude. Right? This is just the magnitude, and now I'm going to get the angle. So this is going to be 300 over 200. And that gives me an angle of 56 degrees. So I can say, therefore, the total displacement is equal to 360 meters. And now we need to say our direction. And if we look at this picture, we're starting in the east direction, turning towards north. So I'm going to write my direction as east, 56 degrees towards north. East 56 north. And there's my final answer. Good. Now, so that shows you that if we have two perpendicular vectors, it's quite easy actually to find their total. But the problem is when we start dealing with vectors that are on an angle. If I'm trying to add this vector plus, let's say, this vector, well, actually those two might be perpendicular. So if I have this vector plus, let's say, this vector, it becomes a lot more difficult to add those together. So to do that, we do what's called breaking the vector into components. So this word components here. So the component vectors, every vector we can break it into two components. So take a look at the right here. I have my total vector pointing off at some angle, and you can see that I can break that into two pieces. It has an x piece and a y piece, and those are two perpendicular components. That's what we're doing here. So our component vectors are going to be perpendicular with an x and a y piece, and they are vectors that add up to the original vector. So what I'm doing is I'm taking a single vector now and trying to break it into two pieces. So we'll take a look at that in this problem. It says break the displacement vector of 30 meters east 25 north down into perpendicular component vectors. So the way I do this, and this is going to be the method that we're going to be using now for just about any vector problem. I draw what I call the crosshairs. You see that I have a cross. And this is x, this is y, and so now I can draw my vector, and it says 30 meters east 25 north, so I have 30 meters, here's my 25 degrees. I'll say that this is 30.0 meters, and that's my vector. You see that I started at the center here, so if I was to draw a second vector, I could draw a second vector off in this direction, or I could draw a vector down like this, or like this, always starting at that center point. So I just have my single vector here, and I want to break it into a triangle. So you can see if I just draw a line, vertical, from the end of it down to the x-axis, you can see that that makes a nice little triangle for me. That triangle looks something like this. 25 degrees. This side is 30. And now I just need to find my x component and my y component. That's what we're dealing with here. And now that x and y, we call this displacement x and displacement y. Okay, and so if we look at that triangle, you can see that the cosine of 25 degrees is equal to adjacent over hypotenuse, so delta dx over 30. And I can rewrite that as delta dx is equal to 30 cosine 25 degrees. And if I put that in my calculator, I get 12.68 meters. Likewise, I can, and 12.68 meters, this is my horizontal component, so you can see that this is going to be facing east. So I've just found how long this piece of my vector is, this piece of my vector. Okay, and now I'm going to find the vertical piece. So I can say here that sine 25 degrees is equal to delta dy over 30. So I can say that delta dy is equal to 30 sine 25 degrees, and that gives me 27. Oh, I'm sorry, my number above, I flipped my numbers. This and this should be reversed. So that first one here was 27.19 meters east, and these are vectors, and this bottom one here was 12.68 meters north. Okay, those are my two components. That's my answer for this question. So we're going to be looking at using that now to add multiple vectors together. Okay, so this idea of breaking our vectors into horizontal and vertical components is very, very, very important, and we're going to be using it very repeatedly. So we're going to see it now on the next page. So this next page says, a cat walks 20 meters west and then turns and walks a further 10 meters south 40 degrees east. What is the cat's total displacement? And notice, I have given us the whole page for this problem, just so we can really space it out and I can show you step by step what we're doing. Okay, so the very first thing that we do here is we draw the crosshairs. Now I can draw my two vectors. So we have 20 meters west. I will draw 20 meters west. You can see, actually I'm going to use a different color just so that it stands out. We've got 20 meters west here. Okay, and now I have a second vector. Well, I can say that this is 20 meters. Now I have a second vector that is going to be 10 meters south 40 degrees east. So 10 meters south 40 degrees east. So I can say that this angle is 40 degrees. Okay, and that's 10 meters. So now my job is to add these two vectors together. And we're going to use our components method. So I want to break up each of these into x and y pieces. You can see that the green one already is just an x piece. There's no y component. So that's going to make our lives a bit easier. But for the red one, I need to make a triangle out of this. And notice that I'm always making this dotted line towards the x-axis. I didn't go this way, towards the y-axis. I went, in this case, up. If I had a vector up here, I would be going down. I'm always going towards the x-axis to make my triangle. So I'll make a little right angle there, and I need to find this angle so that I can use my triangle. So that angle is going to be 50 degrees. You can see that 40 plus 50 is 90. Okay, that's the start of my solution here. So this, I would call this step 1. Okay, and so for this problem, I'm going to label our steps. So we have step 1, step 2, and actually I'm just going to use yet another color for these steps. So step 1 here, step 2. So for step 2, I want to find my total x displacement, and I'm going to want to find my total y displacement. Okay, so the total x displacement is going to equal displacement 1x plus displacement 2x. And the whole reason that we're breaking these into components, x and y, is that then we can add them together easily. All the x pieces are along the same plane, so we can add them together easily. And all the y pieces, we can add those together easily. So, displacement 1x, well, this is going to be, our first displacement was this guy, 20 meters west. All of that is x. So I can say here, this is 20 meters west plus, and now displacement 2x. Remember, if we've got this adjacent side here, adjacent to the angle, I can use cosine. So I'm going to go straight to sort of the solution we had before, where we say the length of the vector, 10, times cosine of 50 degrees. That's going to be this horizontal component. Okay? So that's what we're using here. So 10 cosine 50 degrees. And that's going to be in the east direction. Now notice, I've got west and east. If I want to make these all the same, I need to make them positive and negative, that sort of thing. So 20 meters west, I can call that negative 20 meters, because it's going to the left, and plus 10 cosine 50, and that's going to the right, so that's positive. Okay, if I add those together, I get a total x displacement of negative 13.57 meters. And so my answer is negative, which means that this is 13.57 meters west. Because I said positive was east, negative is west. So 13.57. Let's clean that up. Okay, so that is our x displacement, and now I'm going to find the y displacement. So displacement y is equal to displacement 1y plus displacement 2y. Now this one's going to be easier because displacement 1 doesn't have a y component. So this is 0 meters plus, well, this one's actually pointing downwards, so I'm going to say minus. you see that this is pointing downwards, so that means it's going to be a minus. So minus 10 sine 50 degrees. Okay, so that gives me a result of, for my y displacement, negative 7.66 meters. And again, I've said negative is down, so that's 7.66 meters south. Okay, so I've got two values here. I've got an x piece and a y piece. So that's the end of step 2. Step 3 is to draw the x and y pieces now. So I said that I have 13.57 west and 7.66 south. So I can draw this 13.57 west, 7.66 south, 7.66 south. My total then is going to be like this. So this is going to be my total displacement, and I'm going to need to find this angle theta. There's my right angle. Okay, and we're very close to finishing now. We say step 4. I'm going to say that the size of the displacement is equal to the square root, and here we're using Pythagoras. So I'm saying 13.57 squared plus 7.66 squared. You can see this is why we broke it into perpendicular components. So we could do this nice and easily. So I get 15.58 meters. And then I need to get my angle. This is the tan inverse of 7.66 over 13.57. Notice I'm doing opposite over adjacent for tan. Okay, so this gives me a theta angle of 29 degrees. And now finally, we can call this step 5. We can say our therefore statement. So therefore, the total displacement is, and I'm going to write this symbol again. So displacement, which is equal to 15. Actually, I need to use my correct number of digits. The problem gave me 3, so I'm going to say 15.6 meters, and I have west 29 degrees south. There we go. There's my final answer. So that's the process. Step 1, 2, 3, 4, 5. Alright, and this is a process that you'll have to practice, but once you get used to it, it's actually very intuitive and very easy, very quick to do. But it takes practice. So that's what this next problem is for. I've left the page entirely blank again for you to use the whole page, but I'm going to leave you to try to solve this problem. It says a hockey puck travels a displacement of 4.2 meters south 38 west, and then it's struck by a hockey player's stick and has another displacement, and again you want the total displacement. So it's the same type of problem. Notice that this time both of our vectors are on some funny angle, so you're going to have to break both of them into components. Okay, so I'm going to leave that one for you to try. On the very last page, there's one last concept here that I wanted to talk about, and it is this category of problems called a river crossing problem. So river crossing problems are two-dimensional problems with perpendicular vectors And the important thing in these river crossing problems is that the two dimensions are independent. which means that whatever happens in one of them is completely separate from what's happening in the other. So we're going to take a look at this problem, and hopefully you'll see what we're talking about. It says a physics student hops into her motorboat and steers straight across a river at a constant velocity of 12 kilometers per hour. If the river is 0.3 kilometers across and it has no current, how long will it take for her to cross the river? Well, this is a straight enough problem. We can say that velocity is equal to displacement over time. I can rearrange that to solve for how long it will take. So the time is equal to displacement over velocity. And let's see, we have our displacement is 0.3 kilometers. Our velocity is 12 kilometers per hour. So then I can say that this is equal to 0.025 hours. And if I like, I could write that as seconds or minutes. Let's just do that. We'll do that times. We have 3,600 seconds in 1 hour. So this is equal to 90 seconds. So that tells us it will take 90 seconds for us to cross the river. Now it says that most rivers have a current moving in the direction of the river. The river now has a current of 24 kilometers per hour east, as shown to the right. So this picture showed the first situation. We just drove straight across the river. Now this picture is showing the new situation, where we're still trying to drive across the river, but the river is also pulling us downstream. So, how long does it now take the boat to cross the river? I'm still driving straight across. The river pulls me this way, so I end up going in this direction, but I am going in this direction here at the same speed. I'm still going 12 kilometers per hour across the river. So, in that direction, across the river, nothing has changed. I still need to go 0.3 kilometers across, and I'm going in that direction at 12 kilometers per hour. So nothing has changed, and we can say it's still 90 seconds, because x and y are independent. But now the question is, how far downstream does the boat land? So again, what's happening is my motor, I am trying to drive straight across here, but meanwhile the river is pulling me downstream, so my actual path looks like this. I'm going down and down and down this way, until eventually I hit the opposite shore further downstream. So if I'd gone straight across, I would have been here, but the river pulled me all the way down here. So the question is, how far downstream do we land? And again, x and y are independent, so I can just say that v is equal to displacement over time. So my displacement in the x dimension is equal to my velocity in the x dimension times the amount of time. We already said it takes me 90 seconds to get across. So, and I'm going in the x dimension, the river is pulling me 24 kilometers per hour east. So I have 24 kilometers per hour east, and I'm multiplying that by delta t, which was 0.025 hours. And this gives me 0.6 kilometers east. And that just tells me how far downstream I'm going to be. So you can see that they're separate. Now the final question here says, what is the boat's resultant velocity? So remember, I am motoring across at 12 kilometers per hour here. This is 12. Meanwhile, the river is pulling me downstream at 24 kilometers per hour. And so the question is, if I add those together, what's my total velocity? So this is going to be v, and I'm going to have some angle theta here. So I can say that v is equal to the square root of 12 squared plus 24 squared. using Pythagorean Theorem. So that gives me 27 kilometers per hour. Theta is equal to the tan inverse of 24 over 12. So this gives me 63 degrees. And I can say, therefore, the velocity is equal to 27 kilometers per hour, going in the direction north, 63 degrees east. And always make sure that you're checking that you're writing your directions correctly. I started north, turned towards the east. Okay, and there's my final answer. So there's a few homework problems there. You will have a chance to work on those in class. And I know this was a longer lesson, but it's a really important concept, so please do work at it. Try the problem here on page 3, and if you have any troubles, talk to me in class. Excellent. I'll see you in the next lesson.